All right, let's go through 7B, the ones that people had left blank or question marks by. And so start off, we're going to do one. Review questions. How did the gambling habits of Chevalier de Marais help launch the mathematical study of probability? Well, he was playing this game and he calculated the probability that he would win by on getting a 6 as 1 6 plus 1 6, which plus 1 6, get a 6 in 4 rolls, and that would comes out to be 4 6, and he thought he'd win 2/3 of the time or 4/6 of the time. However, he didn't. He won less than that. People got used to him winning all the time, and so then he changed his game to getting double 6s with 2 dice, and he calculated that that would be 1 out of 36 added however many times he played, and he said 24 times, so I could go times 24, which is 24 36, and he thought he would be safe with that. 4 goes into there and 4 goes into there, or actually, let's see, 6 goes into both of these and comes out 4 6 or 2/3. He thought he'd win 2/3 of the time. He didn't, and so then mathematics started, probability started working, and they realized that it should be 1/36, 35 36 24 times, and that would be not getting double 6s, and take 1 minus that, and it comes out to be about 0.4948, or less than half the time, and he lost money. But that whole investigation about probability got him started. It got probability study of mathematics started. Okay, 2. That was a long-winded answer. You didn't have to put all that down, but I just wanted you to understand it. 2. Give an example of where we would be interested in an AND probability. So the probability of AND would be both things happening. So your parents buy you a car and get you pay your college tuition. That would be a probability you might be interested in. And how do we determine whether the events are independent or not? Well, the probability that your parents buy a car for you probably won't be the same probability if they're paying for your tuition. So they wouldn't be independent. Give examples of each case. So here's non-independence. Now, the probability that the parents love you and the probability that the parents, let's see, are older than you. That one has a very high probability, and it probably does not depend on whether they love you or not. So there would be independent events. Knowing that they're older than you doesn't change whether the probability of whether they love you. Okay? Dependent, independent. 3. Give an example where we would be interested in either or probability. We might be interested, just same thing, probability that they'll buy you a car or pay your tuition. Some of you, you'll get neither, and some of you will get both, and some of us might get one or the other, but not both. And do they overlap? This one, they could. You might have parents that buy a car and pay your tuition, and so these could overlap. Ones that don't overlap might be the probability that you, let's say, go to a dance on Saturday night or go to the movie. Probably not going to do both, since they're at the same time. You're either going to go to the dance or you're going to go to the movie, but not both, and that would be mutually exclusive. This one could be not mutually exclusive. Okay? And so this one, you would do the probability car plus the probability tuition minus the overlap. This one would be just probability dance plus the probability of going to a movie. 4. What is the at least once rule? Explain how the at least once rule used to find the correct probabilities for the games of Chevalier. And that I already did. The probability for rolling 1-6 would be 1 minus the probability of getting no 6s. And to get no 6s on 4 rolls, that's going to be 5 out of 6 chances of not getting a 6. If you do it 4 times, it would be 5, 6 times 5, 6, 4 to, or 5, 6 to the 4th power, 5, 6, 4 times. And you would take it away from 1. This is getting no 6s. Everything else would have at least 1, 1, 2, or 3, or 4. And that's how you would calculate it for that case. And I showed you how to calculate it for the case where he's going for double 6s. That's 4. Now we're to 7. 7 says, decide whether it makes sense. The probability of drawing an ace or a spade from a deck of cards is the same as probability of drawing the ace of spades. The ace of spades is the and. You have to get an ace and a spade, which there's only one way to do that, 1 out of the 52 cards. But the probability of getting an ace or spade is probability of getting an ace, which there are 4 out of the 52, plus the probability of getting a spade, which there's 13 out of the 52, minus any overlap, and the overlap is 1 out of 52. Okay? Let's see if I answered everything. The probability of drawing an ace, is it the same as the other one? No. So you didn't have to do that, because, but that kind of helps explain it. Next one is 9. On 9, we're supposed to, does this make sense? My chance of getting 5 on a roll on a dice is 1/6. So my chance of getting at least 1 5 in a roll of 3 dice is 3/6. That's Chevalier's mistake. At least 1 would be 1 minus not getting a 5, which is 5 6 3 times. Now, yeah, and if I drew a tree diagram, I'm going to get a 5 or not a 5. And this would happen 1/6 of the time, and this would be 5/6 that doesn't. Then I'm going to get a 5 or not a 5. 5 or not a 5. And then again, and this branch would have a 5 in it, this one would have a 5, this one would have a 5, and both of those off of there. And this one would have a 5. If I go up to a 5, the only one that doesn't have a 5 is the 5 6 5 6 and 5 6 chance of not getting a 5, and that's why we do 5 6 to the 3rd. And this is the only branch we don't want. Everyone else has at least 1 5 in it, so we take 1 minus that, and that's the probability. So it's not 1/6 plus 1/6 plus 1/6. It's 5 6 to the 3rd subtracted from 1. Let's go to number 10. Does it make sense? To find the probability of at least one of my 25 lottery tickets as a winner, I calculate the probability that none of my lottery tickets is a winner and subtract it from 1. That is exactly the at least one rule. And so that does make sense. Next one is 14. And 14 says, discovering that your 3 best friends all have a birthday in April. And probability. Determine whether the events are independent or dependent. Okay, so all 3 friends have a birthday in April. If one does, that doesn't change the probability that the second one does or the third one. And the first one has a probability of 30 out of 365. And the second friend has a probability of that. And for and, the probability that both do, you would multiply. And you multiply. 30 out of 365 and then 30 out of 365. Or 30 out of 365 to the third. And that would be the probability all 3 have it. And are they independent? Yes. The one birthday for the second person doesn't depend on whether the first one was in April or not. It depends on when the mother had the baby, not when the other mother did. Okay, 17, next one. See if I got enough room here. Randomly drawing and immediately eating 2 red M&Ms in a row from a bag that contains 8 M&Ms out of 40 total. Well, the probability of drawing 1 red one is 8 out of 40. Then the second one becomes 7 because you ate one already out of only 39 left. And so the probability of getting the second one has depended on whether you got a red one on the first. So these are dependent events, and the probability would be 56 over whatever 40 times 39 is. Okay? 17, let's go to 19. 19, selecting an all women from a 7-person jury from a pool of 15 men and 15 women. And that was to get a 7-person jury, all women. Well, the chances of getting the first woman is 15 out of the 30, but then the second woman, if you got a woman the first time, there are less women, so the probability changes. So that's dependent. It depends on whether you got a woman the first time. Now it's 14 out of 29, 13 out of 28, etc., down until you get the 7 of them. And that's how you do 19. 20. Randomly selecting 3-person committee consisting entirely of Americans from a pool of 12 British and 18 Americans. So consisting entirely of Americans, so there's 18 out of 12 plus 18 is 30. Once you picked one American, there are less of them, and now there's 17 out of the 29 people left, so the probability of picking an American has changed, makes it dependent on what you picked for the first one. And you'll do that, you continue this pattern, 16 out of 28, 15 out of 27, till you get your 3-person committee, which would be just one more, 16 out of 28. There's the 3 Americans, and that would be the probability of getting 3 Americans. These are both dependent. (22) Either or probabilities, getting a sum of 6. No, wait a minute. 22. Sum of either 6 or 8. Sum of 6, sum of 8. And of course on the dice, Sum of 6 is 1, 5, 1 and a 5, 4 and 2, 3 and 3, 2 and 4, 1 and 5. There are, sum of 6 is 5 out of 36. Sum of 8 is 6 and 2, 3 and 5, 4 and 4, 5 and 3, and 2 and 6 or 6. Anyway, we got those, and there's 5 of those. And we would add these two and subtract any overlap, but these don't overlap, and so to be 10 out of 36 for the probability of getting one or the other. And the point here is that to do or, you add, except you would subtract any overlap. Stuff that you would count twice. 23, so now we're drawing a red 6 or a black 5 on one draw from a deck of cards. Drawing a red 6, so that's 26 out of 52, or 1/2. Half the cards are red. Oh, red 6, so there are 2 red 6s out of the 52. I did red, but not red 6, there's only 2 of them. 6 of hearts and 6 of diamonds. Or a black 8, so that would be 8 of spades or 8 of clubs, 2 of them. Minus any way to get both of those, which there is no way to get a red 6 and a black 8 with one draw of one card. So we don't have to subtract any intersection, and there's 4 out of 52, or 1/13. Okay, now we're to 24. Drawing either a jack or a spade from a regular deck. Probability of drawing a jack, 4 out of 52, because there's 4 jacks. Drawing a spade, there's 13 out of 52, minus any overlap, and there's 1 jack of spades, so we have to subtract it because we counted it in here and we counted it in there, and we don't want to count it twice, so we subtract 1, so we got 17 minus 1, 16 out of 52. Okay, 25. 25, selecting 3 fully charged batteries in a row from a large batch of, so if it's a large batch, the probability doesn't change. It says 5% are dead. So drawing a fully charged, that's 95% are good, so 0.95 or 95 out of 100, or 1/1920, that would be, if you did in fractions. And if you're going to do 3 of them, you would take it to the 3rd power, and that would be the probability of drawing 3 fully charged out of when there's a large number of them and 5% of them are dead, meaning 95% of them are good, fully charged. All right, I'm going to stop there and go to let's go to 26. 26, and then I'll stop. That looks like, or 27, 28, those are 29. They're all in the same section here. No, they're not. 26 is. So 26, randomly meeting 3 international students in a row on a campus where 1 in 12. 3 in a row, so there's 1/12 chance of meeting one of them. And to meet the second one, we'd have to multiply by this itself, or 1/12 times 1/12. But to meet 3, we take it to the 3rd. And so that's 1 to the 3rd, or 1 over 12 to the 3rd, which is a number you can calculate in a calculator. Okay, I'll stop there and do a second video for the second half of this.